the next minute, I will talk to you a little bit about the work I've been conducting on longitudinal data in collaboration with Mauricio, Álvarez, and ADSAI. And I'll try to give you a few insights on how deal with longitudinal, a whole bunch of longitudinal data with GPs. So as we have seen just before, Gaussian processes are really elegant tool to more longitudinal data. And nowadays, it's generally straightforward to fit a GP on very large number of observation or handle a few correlated time series with like multi-output or multi-task model. And we can do really more complicated things like we've seen before. The problem is, what do we do when we have millions of correlated time series? We've seen it with GPs. We have a cubic computational cost in the number of observations, and we can still model directly correlations between different time series by defining like an explicit correlation matrix, but it can scale really, really badly. On a project or illustration, I will talk to you about the data that we have on children in Singapore. In this kind of data set, we observe 300 individuals, 300 children, and for each of them, we have like 700,000 time series, which correspond to gene-related information, namely, we have methylation value, which is basically for you, for us, a number between 0 and 1. And all of those, for all of those persons, we have an information that is observed for a handful of timestamps, like we observe between birth and during the childhood gene-related values. And how do we deal with those? How do we share information for all those different sources of correlation? Because we have correlation between individuals and genes. I have illustrated this with a few of those, like you have several individuals and several genes, and you can see that it's a lot of time series, and it's just a really, really tiny example of what we have for real. First, a little bit of context. I will talk to you about the core of the model that I came up with during my PhD. And it's based on the framework that we've called Magma, sort of acronym for multitask GPs with a common mean. And it's really interesting because what Virginia talked a little bit before about was kind of an idea that is similar, which is we can share information between different time series by defining a common mean process, which is unobserved. And if you look at the first equation, we say that yi, which is our curve, is defined as a common mean process that is shared by all individuals plus a perturbation that is specific to one individual and a Gaussian noise. If all of those quantities are Gaussian processes, we have that if we know the latent mean process, we're still Gaussian. And this model is at the basis of the framework, which gives us, as I told you, one really nice feature is that this model naturally handles irregular grids or measurements, so we don't have problem with missing data of those kind of things. Of course, I will skip all the mathematical details, so you can just go to the paper for that, but we have a way to learn the hyperposterior distribution of the mu0, which is unobserved, and we can still learn all the hyperparameters as well, so with a NIEM algorithm. And because I skipped all the details, the best way to visualize those are a little graph or GIF in this case. On the left-hand side, you can see a traditional GP. If we observe a few data points, like let's say 5, and we try to forecast time series in the future, you see that when you don't have data points, you quickly dive to the prior, which is here 0. So we are really limited in your prediction, your really short-term predictions. And as you collect more information, you're able to do more meaningful prediction. But on the right-hand side, you can see with Magma, the little colorful dots are the observation from other individuals. And because you've learned the dashed line here, the dashed curve, is a mean process, the latent mean process that you learned during training. And even at the beginning, you can see that you're doing meaningful prediction, even though you don't have any, you don't have observed yet the future, of course. So for new children observed between 10 and 12 years, about that, you're still able to do meaningful prediction, make meaningful prediction for the future. An extension that we've been proposing is adding a clustering structure on those data. I'll go really quickly about that, but if you're adding some multinomial prior distribution, you can come up with a mixture of Gaussian processes. This is really interesting because often in those kind of data, defining only one mean can be really restricting because you can have different cluster structure, as you can see here. So if those example, you have, as you can see, call for data, and you can really identify that we have 3 different groups. And in this case, with the algorithm, you can simultaneously train the hyperprocedure distribution and hyperparameters that I talked to you about, but you can also cluster the different individuals at the same time. And by doing that, you can identify that the black dots, which are the observation, belongs to one cluster. They look like different individuals. And on the left side, you have Magma, the previous algorithm that I presented you. But with the version with the clustering, you're able to identify this cluster structure, and you're providing much more like accurate predictions and a clustering information at the same time. So all of those are implemented in our package, which gives us the framework that leads to our problem. So the problem that I presented before is way more complicated. These examples were just in one dimension, like you have multiple individuals, but you observe only one variables at the same time. Let's say, sorry, just one gene. But now we have multiple sources of correlation. We have the individuals and the genes, and we can imagine many different sources of correlation as well. So simple way to model this would be to define, like for I, which it denotes still the individuals, but J now denotes the genes. We can just add another perturbation, like we still have a mean process and a perturbation for the individual, which individual we're looking at, but we can also look at a specific gene and a noise, but we can model as we want. In this case, we just add this all new GP, and we still have likelihood that would be Gaussian, but we have a problem because what is a mean process like for in this case? We don't have like a natural mean process. We have a bunch of them. Actually, we can average over the individuals, we can average over the genes, and both those ways make sense actually. And we can also average on everybody. So what would be the mean process we want to go to when we don't have information for our children? The thing is, we can do it meaningfully by computing the posterior distribution on the subset of the data that we care about. Like if we want to a specific mean process for one individual, we can average over all the all the genes, sorry, for the individuals, and we can do it also if we fix the gene. We can average over the individuals, or we can do on overall. I don't know where about timing, but if we want to visualize that, I plotted a little example with only 3 individuals and 2 genes. But the thing that you can see with the dots here, the observation that we have are the 2 big black dots, and we want to predict the yellow dots on the right side. Yeah, we can do it quite meaningfully because we dive to the informed prior. And on another example, if I change my gene with triangles now, I adapt my prediction to go to the true value. And with those adaptive prediction, depending on the individual or gene, you can still have meaningful prediction for no matter the number of sources of correlation that we have. Thank you for your attention, and this is the answer to your question.